All right, let's get started. Today, we're diving deep into one of the biggest questions ever. What is everything really made of? We're going on a journey through time to understand the atom, the fundamental building block of our entire universe.
I mean, really think about it. The device you're watching this on, the coffee in your cup, the air you're breathing, what is all this stuff really? It's a question that has puzzled the greatest minds for thousands of years.
And the answer, of course, is the atom. Now, the story of how we figured that out, well, it's one of the greatest scientific detective stories of all time. And trust me, understanding the atom is literally the key to understanding, well, everything.
So here's our game plan for this explainer. We're going to start at the very beginning with the first real theories. Then we'll follow the clues, piece by piece, through some absolutely game-changing experiments, all the way up to what we know today and, why it actually matters in your daily life.
And here are the main characters in our story. You've got Dalton, Thomson, Rutherford, Bohr. Each one of these scientists added a crucial piece to the puzzle. Sometimes they built on what came before, and sometimes they just blew it all up and started over. This is going to be our map for the journey.
Okay, so let's start our quest right at the beginning. Every massive scientific revolution has to start somewhere, usually with one simple but powerful idea.
And for the atom, that idea came from John Dalton way back in 1803. He imagined atoms as these tiny, solid, unbreakable spheres. Think of them like super, super tiny billiard balls. It was a really simple idea, but you know what? It was brilliant. For the first time, it gave a good explanation for how chemical reactions actually worked.
And that's what science is all about, right? Dalton's model was a huge win because it explained so much, but it had a major flaw. As scientists did more experiments, they started finding clues that these indivisible little balls might actually have even smaller pieces hidden inside them. The plot thickens. And that brings us to the next chapter of our story. This is where that simple, solid billiard ball idea starts to completely fall apart, all thanks to the discovery of the first piece inside the atom.
Right, so meet J.J. Thomson. He's messing around with these things called cathode ray tubes, and boom, he discovers this teeny, tiny, negatively charged particle. He calls it the electron. This was a huge deal. So to explain it, he came up with the plum pudding model. Just picture a ball of positively charged dough, that's the pudding, and then you've got these little negative electrons stuck all through it, kind of like raisins or plums.
Now, this was a massive leap forward. We finally knew for sure that atoms weren't just solid balls. They had parts. But, and there's always a but, Thomson's idea of how those parts were arranged was about to go head-to-head with an experiment that it just had no chance of surviving.
Okay, this is where our story gets really good. I'm talking about one of the most shocking and important experiments in the entire history of physics. Seriously, this experiment was a complete game changer.
So Ernest Rutherford decides he's going to put that plum pudding model to the test. The plan was pretty straightforward. Shoot a bunch of tiny positive particles, they're called alpha particles, at a piece of gold foil that was unbelievably thin. Now, if the atoms were just soft pudding, those particles should have just blasted right on through, no problem.
But that's not what happened. Not at all. I mean, yeah, most of the particles zipped right through as expected. But every once in a while, one would get knocked way off course. And this is the crazy part, some of them actually bounced almost straight back, like they hit a wall.
I love this quote from Rutherford himself because it just perfectly captures how completely shocked everyone was. He said it was like firing a cannonball at a piece of tissue paper and having it bounce back and hit you. It was just impossible. Something hard and heavy had to be hiding inside that atom.
So to explain this absolutely bonkers result, Rutherford came up with a totally new model. He realized the atom had to be almost entirely empty space. And at the very center, there had to be a tiny, super dense, positively charged thing he called the nucleus. The little electrons, they must be orbiting way out on the edges, kind of like planets zipping around the sun.
But of course, solving one puzzle just created another one. See, according to the physics of the time, an orbiting electron should be giving off energy constantly. That means it should spiral into the nucleus in like a fraction of a second, and the whole atom should collapse. But obviously they don't. Atoms are stable, so what on earth was going on? The answer came from a guy named Niels Bohr, and his solution was genius. He brought in some weird new ideas from this field called quantum mechanics. He suggested that, well, maybe electrons can't just orbit anywhere they want. Maybe they're stuck in specific energy levels, like lanes on a highway. They can't exist in between the lanes.
And to jump from one lane to another, they have to make a quantum leap by absorbing or spitting out a perfect little packet of energy. And Bohr's model was amazing. It totally solved the stability problem, and it perfectly explained why hydrogen gives off its specific colors of light. It was a huge breakthrough. But, yeah, you guessed it, it wasn't perfect. The model started to break down when you tried to apply it to more complicated atoms. The picture just wasn't quite complete yet.
All right, so that brings us to the final stop on our tour, the model we use today. And this is where things get really, really weird. We have to let go of those nice, neat little orbits and embrace something a whole lot fuzzier.
So here's the last big mental leap we have to make. Thanks to quantum mechanics, we now know that it's literally impossible to know an electron's exact location and its exact speed at the same time. The more you know about one, the less you know about the other. So that whole idea of a neat little planet on a predictable path, we had to throw it out the window. It's all about probability now.
Which leads us to the modern idea of the electron cloud. Now, it's not a real cloud of fluff. Think of it more like a probability map. It just shows us the areas around the nucleus where you're most likely to find the electron at any given moment. Where the cloud is thicker, the probability is higher. It's not a path, it's a smear of possibilities.
So wow, what a ride, right? From solid little balls to these fuzzy clouds of pure probability. You might be sitting there thinking, okay, that's a cool story, but why does any of this matter to me? Well, it turns out understanding the atom has changed pretty much everything about our world.
I mean, seriously, look around you. This fundamental knowledge is the foundation of almost all modern technology. Medical scans like MRIs that let doctors see inside your body, that's atomic science. The computer chips and semiconductors in your phone, your laptop, everything, that's all based on this. Nuclear power, designing life-saving medicines, creating new materials, it all comes back to knowing what an atom is and how it works.
And that brings us to the end. But it's really not the end of the story, is it? The journey of discovery never really stops. As our technology gets more and more powerful, it just makes you wonder, what else are we going to find out about the atom? What new, mind-bending discoveries are waiting just around the corner? It's pretty exciting to think about.